of Toronto in the Department of Computer Science and the Department of Statistical Sciences. He is a faculty member of the Machine Learning Group and the Vector Institute and the CFAR Chair in Artificial Intelligence. And he was a postdoctoral researcher at Microsoft Research, New England, and he did his PhD in statistics at Stanford University. And he has a master's degree in computer science from Stanford as well. Welcome. Thank you for accepting our invitation, and stage is yours.
Thank you for the kind invitation, and thanks everyone for coming to the call. So today I'll talk about feature learning, two-layer neural networks, and this is a it's like a kind of a combination of 3 papers that I've done in the past two years. So I want to particularly focus on how different data structure actually affect the learning dynamics with neural networks. Just a heads up, it'll be a theoretical talk, and the goal is to explain why neural networks work in practice and compared to like the classical models and the kernel methods. And I will focus on these 2 questions. And this is the first one is, why do neural networks learn useful features? I'll elaborate this question a bit better later on. And the second question is, how does different data modeling assumptions actually enter into learning dynamics? So this is kind of the focus of the talk. I think there's somebody waiting in the waiting line. All right, so let me formalize the setup. So I'm going to focus on a supervised learning setup. That means that there is input, which is xi. This is d-dimensional input. And there is a target function, f star, and some noise, epsilon, and the response is yi. So you can think of xi as the pixel values and yi as the label of the image. Could be cats and dogs. And then there is some label noise here. But this is just the classical supervised learning setup. And the target f star is unknown. So that's what we're trying to learn with the neural network. And whenever there is a target, there is a star in a quantity, that means that it's unknown and that needs to be learned. Okay. And the learning basically is we take n data points and try to minimize this empirical risk. And that's under the squared error law. So here, f could be any model that I choose. For example, I could pick linear model, I could pick neural network, I could pick kernel method, and I'm going to minimize this over f, and that's going to be my student model. The teacher model is what generates the data. That's what we're trying to learn. So to assess the performance of what we have done in this learning procedure, we look at the prediction risk, that is the expected squared error loss between the function f that we learn, kind of output of the two-layer neural network, or kernel methods, or linear model, and the true function f star that needs to be learned. If this is small, then I'm doing well. If it is not small, then my model is doing poorly. It's basically the test error actually in practice. It's what we call test error in practice. So I want to stick to the proportional asymptotic regime. So what is that? That means that the number of samples n is proportional to the input dimension d. So this is basically saying that the ratio n over v converges to a constant denoted by discrete letter psi. It's ranging from 0 to infinity. If this is large, that means that the number of samples is actually much larger compared to the dimension. If it is small, the other way around. But it's important that it's the proportional asymptotic regime. That means one of them is not a polynomial in the other. They are linearly scaling according to each other. So why is this interesting? Well, I will argue that it's kind of what happens in practice in general. The proportional regime is quite relevant, but the real reason that this is interesting is it will allow me to compute this test error, the prediction risk, precisely. It's not going to be an upper bound. It's going to be a precise calculation of the risk, and it is possible in this regime. So that's the main motivation, actually. It's good to keep in mind this parameter psi, actually, that Greek letter. So large psi means large sample size compared to the dimension. So this will come up a lot, and I'll use it as basically one quantity that's it's good to memorize what it is controlling. I'll remind you later. So I want to simplify this problem setup. So instead of learning any generic function f star, the target function that I will consider is of the following form. So this is in statistics, this is called single index model, but you can think of it as like a simplified version of a neural network. So there is a linear part that is the inner product of x and beta star. And then there's a nonlinearity on top, that is sigma star. Now, star entities are unknown. Both beta star and sigma star is unknown. So what is special about it is basically nonlinearity is a one-dimensional function, and output depends on the input only through this direction beta star, which is also unknown. Okay. We need to learn both sigma star and beta star. And how does so the input in this case, I'm going to assume that it's a multivariate Gaussian with some covariance matrix sigma. So I will consider three different covariance models. And the first one is basically identity covariance. So this is what we call the isotropic data. There is no structure in the covariance. It's just an identity matrix. If you look at this picture, that's the blue contours are the distributions of the input. There's no structure, no ellipsoid structure. That's identity covariance. And the beta star, I also put in the same figure. It's a unit vector in some direction. So the point is, input does not contain any information about the target beta star. Perfectly uninformative case. And then on the other extreme, I will assume that the covariance satisfies the following spike structure. It's now identity plus theta, a real number, times mu transpose. Mu is again a unit vector. Theta controls the magnitude of the spike. Now, if you look at the figure, the direction of highest variance is mu, exactly aligns with beta star. So input has a lot of information already about the target. This is an idealized setting. This would not happen in practice, but I will use this to demonstrate how neural networks adapt to this structure more efficiently than other models. And then I will interpolate between these two extremes. So one left one was the uninformative input. The right one is, the middle one is actually too much information contained in the input. And now I'll interpolate between these two. Now there is some information in the input. So you see that there is some angle between mu and beta star, but the alignment is not perfect. So the questions is basically questions I want to answer is, how does this spike magnitude, which is controlled by theta, and how does the alignment between mu and beta star, the angle between these two unit vectors, actually determine the performance of neural network? How do these parameters affect the performance of the neural network? Are there any questions about the problem setup?
So we want the middle one, but it never happens. So we try to approximate it with direction.
Yeah, so middle one, well, actually, if you have the middle one, that's a very good setup, but that will never happen. But I will still assume it happens and try to explain stuff. But the right one is actually more realistic. Why does this happen? So I'll give you an example. Maybe in like if you open any applied statistics book, the input is very high dimensional. What is recommended is you would do PCA, reduce the dimensionality of the input, and then regress your Y onto those like first few principal components. So that is the first principal component actually. But if you do like first few, that's a realistic setting, but this is an idealized setting. So it's kind of like a toy model that captures that relationship. Okay, so I will consider two different models. The first one is my baseline model. So what I'm going to focus is two-layer neural networks or neural networks, why they work better. But what am I comparing against is the kernel method. So that's the kernel ridge regression, which is my baseline model. The first one is the random features regression. I basically choose a feature map that takes my input X and transforms that according to that following function. So what is that function? W0 is some random matrix that multiplies X, and then I apply a nonlinearity sigma. That's the activation function. So, and then after getting this feature map, I'll minimize the ridge regression objective. And this has a very specific form, I agree, and I'll justify it in the next slide when I talk about neural networks. So let's just say this is the random features regression. Well, I could also just do kernel ridge regression, just pick an RKHS or a kernel, do this minimization over the RKHS, and be happy with it. So these are models that are understood very well in learning theory. For example, what you're seeing on the right figure is the double descent phenomenon, which basically non-monotonic risk. And you can compute these precisely for these models. But what is missing in these models is basically there is no feature learning. What does that mean? You fix a feature map, and then that is fixed throughout the training, and then you train your model with this fixed feature map that you actually pre-designed. Now let's talk about two-layer neural networks. So what you're seeing on the right as a graph is the two-layer neural network. You have the d-dimensional input. You multiply that input with a first layer weights. You apply nonlinearity, and then the second layer weights, and then you get to the term. So in matrix vector notation, the display equation is basically how I would write a two-layer neural network, right? Now, what is important is when you train a two-layer neural network, you train first and second layers, both of them. Now, let's think of a training scenario. I would initialize both weights, W and A. W is the first layer weights, A is the second layer weights. Now, if you look at this display equation, you can think of the output of the first layer, basically output of this much as my feature map, right? It takes the input, generates these features, and then you train, if you minimize current error loss, you're training a ridge regression on top if you're minimizing the second layer. So you're basically, if you're training the first layer, W, you're training the feature map. If we did not train the feature map, keep W at initialization, which is random. Now let me take you back. That is precisely this random feature map that I constructed. So what I will do is I will compare the performance of this random features regression to the trained two-layer neural network. And the difference is basically whether the first layer is trained or not. Okay? So minimizing it over second layer weights is a strongly convex problem. It's quite straightforward, but there is no feature map. So if we train the first layer weights, there is feature learning. So that is what is actually important. And we want to demonstrate this effect. How do we do it? We train the first layer weights using gradient descent. There is now feature learning, and compare that against the risk of the random features regression. And if we do better, that's great. We show that feature learning is actually beneficial. But the question is whether we do better or not. Is the problem set up okay? Okay. Very simplistic problem set up, actually. Okay, so how does the learning work? Well, it's quite straightforward, actually. So I'll simplify the learning so that I can analyze it mathematically. And the learning in two-layer neural networks has two parts. First, you take one gradient descent iteration on the first layer. You can actually take a few iterations on the first layer. That's perfectly fine, but one gradient descent is also fine. So take a few iterations on the first layer, and then train the second layer, minimizing the second layer weights entirely. So you can also do like approximate minimization. You can run SGD on the second layer or gradient descent on the second layer. That's fine, but those are just going to add extra complications, but it's perfectly fine to analyze them. So they're not going to create too much difficulty. But what is important is we train the first layer weights, and then we train the second layer weights. It's a stage-wise training procedure. This is not what you would do in practice. This is to analyze it, to be able to analyze it mathematically. Okay, Then we take the neural network function and compute its risk and compare that with the risk of random features regression or risk of kernel methods. The risk of the kernel method would basically be the same thing except that W1 is kept at W0, and then you would be basically getting the random features regression. So we can actually compute both of these risks precisely, and actually their difference precisely too. So that will give us how much feature learning actually helping in this calculation. Okay. So I will make a stronger baseline, actually a stronger statement on the kernel method. So this is going to be like a very precise baseline for neural networks to succeed. So here is a setting in the isotropic case. So take a function f star, that's the function you're trying to learn, and write it as a linear function plus its nonlinear component. So this is like an expansion that I'm not going into too details, but it's like think of it as a Taylor expansion, but it's just a linear part of this function and whatever is left as nonlinearity. Now, there are existing methods that says that if the input is isotropic, risk of these kernel methods are lower bounded by the L2 norm square of the nonlinear part. Okay, so this is like this appears in many of the recent papers. It's just a lower bound on the risk of kernel methods. But what does learning mean? If I want to learn F star, learning means that the risk needs to go to 0. The prediction risk needs to go to 0. But this is a lower bound. So what is it telling me is that for a kernel method or a random features method to learn this function F star, you need to have this part 0, right? And when is the nonlinear part 0, it's basically when the function is linear. So in the proportional regime, when n is comparable to d, a kernel method can only learn linear based on this lower bound. So this is a very good baseline now. And whenever I show you a figure like this one on the right-hand side, and there's a horizontal dashed line like this, that is this lower bound. So this dashed line is the kernel lower bound, and if we go below that, if we can show that neural networks actually do, the risk of the neural networks go below that dashed line, that means that neural networks are doing better than kernel methods. So that's a very good baseline for us to work with. So that's the goal. Okay. So let me present some formal results. So I'm going to assume a non-degenerate target function. So this I will talk a bit more about it. It's actually quite important, but for now, we just assume that the expectation under the Gaussian measure of the sigma star, the first derivative of sigma star is non-zero. So that's some non-degeneracy assumption that I'll talk a bit more about it later. And then we have the standard Gaussian initialization. So here's the summary of the results. Okay, so here is my kernel lower bound, this dashed line. Is here. So the yellow, the topmost curve, is the risk of the random features regression, risk of the kernel method. So you can see the double descent very clearly, actually. So that's nice. And then if you train your features, you do two-layer neural network with a small learning rate. That is this middle curve, the purple one here. It maybe pink. I don't know the color here. Maybe magenta. Okay. So, but you see, it improves the risk if you train with a small learning rate, but it's not able to go below the kernel lower bound. Now, if you train with a large learning rate, that also corresponds to taking more iterations, then you are able to go below the kernel lower bound. That is the purple curve now. And basically you're learning nonlinear functions. So summary is as follows: small learning rate still improves the risk, but not able to learn nonlinear functions. you need to take large learning rates so that you go below the kernel lower bound, which is like a limitation of the kernel left methods, so you can beat that threshold. Okay, so this is a summary of the result. Now, why does this happen? Okay, well, it actually happens because when you take a gradient descent iteration, you're learning quite a bit on the unknown quantities. So let's look at the eigenspectrum of the learned first layer weights. I'm just going to look at the eigenvalues after taking one gradient descent iteration. So here's the problem setup. I have an activation that is 10H. The target is a ReLU of inner product x beta star, and beta star that is unknown is proportional to -1 first half and +1 second half, normalized to have unit norm. So if you initialize your first layer weights W and look at this eigenvalue spectrum, since it's a Gaussian matrix, you're gonna see this distribution. So this is going to be its eigenvalue structure. So this is called, this has a name that doesn't really matter too much in this context, but it's the Marchenko-Pasteur law. And if you take one gradient descent iteration, a spike will appear in the spectrum. So after one gradient descent, this is what you're seeing. This is now the largest eigenvalue. So that's the effect of the gradient descent. Now, if you look at the eigenvector corresponding to this eigenvalue, now we're going to look at the subfigure here. The dashed line is beta stars. First half -1, second half +1, and normalized to the unit vector. So the dashed line. And the eigenvector corresponding to this largest eigenvalue aligns with this unknown target. So after gradient descent, actually, you already learned the unknown direction in the target. So that's quite a bit of information. So that's basically quite useful. That's where actually the usefulness of future learning comes from. All right. So summary is basically the bulk of the spectrum. The Marchenko-Pasteur law is unchanged. But if you have a strong enough, if you have a large enough signal, which will be related to the learning rate, then a spike will appear, and that spike will actually be aligning with the target unknown direction beta star. And that's a useful feature learning part. Okay, so this is actually there's a formal statement of this, but here's my simplification. And for the formal statement, you can check the paper, and the colored names are the student authors of this paper who have done a fantastic job. So here is kind of an informal statement. Let U1 be the leading singular vector of W1, the eigenvector corresponding to the largest eigenvalue. Okay, and you have a learning rate eta, so this is the step size in gradient descent. If it is larger than a threshold, a spike will appear, and this spike will give you better alignment if you have large sample size. So I'll show this on the figure. X-axis is the learning rate, eta, and the y-axis is the overlap between the eigenvector and the unknown beta star. Okay, so if you look at this figure, see if I can actually. If you look at this figure, if the learning rate is small, you see there is no overlap, right? So you start increasing your learning rate a bit, and then at some point, there is a phase transition that you're now able to detect the signal. Now you're having a non-trivial overlap at this point, and as you increase the learning rate, the overlap keeps increasing. Now, different curves correspond to different values of this parameter psi. So it's basically dimension is kept constant, and I'm increasing the sample size. So brighter the curve is, larger the sample size. So you can see that it gets better with large sample size. So you're going to have better alignment. So sample size actually helps. It helps in this case. Okay. Still not talking about the learnability part, what I demonstrated here is why feature learning might help. Well, it is getting this unknown beta star to some extent. It is recovering it to some extent. Still no learnability or comparison with the kernel methods. Okay. Now let's do a bit more than that. And this is basically the theorem that talks about the learnability when you take a small step. Remember, small step is not going to be sufficient, but it will still be good in terms of feature learning. So here is the formal result. We compare the risk of a kernel method and risk of a neural network. One with feature learning, that is neural network. The other one is without feature learning. Difference between these two is called delta. Larger the delta is better the improvement, right? So we want delta to be large. So it turns out we can actually compute this delta precisely. It's like a bunch of ugly math equations, but it has some nice properties, and that's what I'm going to show you here. Delta is always non-negative. So that means that if you take a gradient descent iteration, you can never make it worse. It's always good to have feature learning. So the brighter the curve, larger the step size. So if you increase the step size, your risk curve is decreasing and decreasing all the way. That's a good thing. So you're always improving. But and also, if you have larger step size, it's always going to improve, but you're always limited by the kernel lower bound. So this kernel lower bound dashed line, you cannot go below that with a small learning rate. You will always improve your risk curve, but you will never be able to go below the kernel lower bound. You're never better than the best kernel method. But we know that neural networks are better than kernel methods. So that's what we need to actually actually talk about. And here's a reference for UL's paper that you guys know. Okay, so this is based on Gaussian equivalence. It's Gaussian equivalence of the learned kernel actually after taking a bunch of iterations. But it's precise asymptotic, it's nice math, but it doesn't actually explain why neural networks are better than kernel, because I'm still above the kernel lower bound. That's what we need to be. And now I will take a large iteration, like very large gradient descent step, and then that'll help in beating the kernel lower bound. But there are pros and cons. The pro is, well, the learned kernel will be nonlinear. That's a good thing. A con will be that we will no longer be able to compute this risk precisely. So precise calculation is no more, but we will be able to go below the kernel lower bound. So here is the result for that. After one gradient descent iteration with a large learning rate, the risk is upper bounded by some parameter tau star plus something that goes to 0 with large psi. So I have control over psi, right? So this Greek letter psi, if I choose a large sample size, I can make size as small as I want. But I need to show that this tau star is smaller than the kernel lower bound. That's what I'm going to do. Basically, compute this upper bound tau star, show that it is smaller than the kernel lower bound. And by just increasing the sample size, then I'll be able to actually beat the kernel methods. Okay, so this is kind of good. Somewhat unsatisfactory is you need to compute this tau star for a specific activation target pairs. So here is what we do, like for example, for 10H or error function, we compute these, and then you can see that you can show that you are able to beat the kernel lower bound. And if you look at this figure, you're going to notice that it's actually rate here is exactly 1 over psi. So that suggests a learnability definition. Okay, so this is kind of the one of the main results that shows neural networks are able to beat kernel methods and learn nonlinear functions. Because if you take a large step, you are able to go below this kernel lower bound. Okay.
I didn't understand psi. Is it something that we define for the upper bound or
Which one, which part?
psi and tau?
Yeah,
actually?
yeah, so well, psi is, the ratio of n over d. Right, so psi is n over d, right? So if I choose a large sample size, then I am able to basically, have control over psi. So like, just basically, bigger data helps in this case, that's what it is saying. Tau star, I didn't show you, but it is a function of, target and the activation function. So you need to compute it. There is a formula. You need to compute it for specific target and the activation pairs. But it's like that computation is not hard. But so the unsatisfactory part is it is specific to target and activation pairs. So like you need case by case. Yeah.
Derived by.
Yeah, so that is not satisfactory, but still gives you learnability for these pairs, for example. So I computed them for these examples, and this is what you get. Good,
Is
yeah.
it true that like I'm understanding something like this? As you increase the sample size and you can increase the step size and perform better.
Yes,
Go
exactly.
below that line more
Yeah.
and more.
Yeah. Well, sample size also will help in the previous case, but you will never be able to go below the kernel lower bound if the learning rate is small. Yeah, you're still in the linear regime. You're not able to learn nonlinear functions. But if you take a large step and increase the sample size, then the risk goes to zero, so you can learn nonlinear functions.
Can we check the last step?
I don't know. But so this learning curve, if you look at this orange line, that tells me that if I increase psi, I can make it go to zero. So here is my learnability definition. If I can increase this parameter psi and make this risk as small as I want, then I'm going to say I'm actually learning. This is my learnability definition. Okay. If I can make the risks arbitrarily small just by increasing the parameter psi, basically the number of samples, then I'm saying I'm able to learn this function. So here is the second problem setup, the idealized setting, where now the input has a spike covariance model. There is some covariance structure in the direction of beta star. So it's the idealistic setting. And the spike magnitude is controlled by theta. And the teacher model is basically the same model that I need to learn. But I want to learn a degree P polynomial in this case, even with kernel methods. Now remember the kernel lower bound. What I showed you under isotropic input, under identity covariance, was that kernel methods can only learn linear functions. So if I want to learn a degree P polynomial, P has to be 1 if I have theta equals 0, okay? If the input has identity covariance, P has to be 1 for kernel methods, because they're only able to learn linear functions, right? Now, the question that I want to ask is, I now added an extra structure into data. Now, despite covariance, there has to be something different in this case. Whether kernel methods actually benefit from this additional spike case, can they learn a more complicated function than a linear function? Can they learn a polynomial? Or what happens to the learning by neural networks? Do they actually adapt to this lower range structure more efficiently than kernel methods? So those are the questions that I want to answer. All right. So now back to this non-degeneracy condition that I actually made in pretty much the beginning of the talk. So we assumed that the expectation of, well, expected value under the Gaussian measure of the first derivative of the target, sigma star, is non-zero. So what this means is I'm going to make a formal definition here, and then I'll give you an example. So it's fine if you don't follow this definition or you don't buy it, that's all right. But this is kind of quite important, so I wanted to make this definition anyway. So this is equivalent to taking this target function sigma star, writing out its Hermite extension, and saying that alpha 1 star, the first coefficient is non-zero. That's equivalent to that. So this Hermite extension is some sort of extension, like a series extension, basically like Taylor series extension, and that you write using the Hermite polynomials. You can generalize this, and that definition leads to the information exponent. So this is a complexity measure, just like, you know, complex, like a polynomial degree of a polynomial. This is another complexity measure. So information exponent of sigma star means that smallest k such that alpha k star is non-zero. Smallest non-zero Hermite coefficient order is what we call the information exponent. Okay, so this is the formal definition. But if you didn't buy this, here is the example. And this is fine to keep in mind and get through the rest of the talk. Now, assume that the target function I'm trying to learn is the following polynomial. Now, this is a degree 5 polynomial, and you can write it as Hermite degree 5 plus Hermite degree 1. Since the smallest order Hermite coefficient, you see that Hermite degree 1, so information exponent is 1. And the polynomial degree is the largest monomial order, that's p equals 5. So it's a degree 5 polynomial with information exponent 1. If you look at the previous definition, the only thing you need to remember about this definition is that information exponent is always smaller than equal to the polynomial order. So p is greater than equal to k. That's the only thing to keep in mind. With that, so let's just remember some results that we already talked about. If the input has identity covariance in the proportional regime, kernel methods can only learn linear functions, so p has to be 1. We already covered this. And it turns out there are existing methods that neural networks with gradient step can only learn functions with information exponent 1. So p and k can be 1 if there is no covariance, but if you add covariance structure, that actually changes quite a bit. So here is the result for that. Now, I'm going to consider a degree p polynomial with information exponent k. Keep in mind, p is always greater than equal to k. Now, the first result says the spike magnitude needs to be of this order so that kernel methods learn this target function. Okay, but this is an if and only if statement. So if the spike magnitude is smaller than this, kernel methods probably fail. That's pretty important to draw the separation line. And the second result says a two-layer neural network with one feature learning gradient descent step can learn this target if the spike magnitude is this much. Now, I know the relationship between P and Q. Sorry, P and K. P is greater than equal to K, right? Now, just by looking at that, I can actually draw a separation. So let me just show you on the figure. Since I know K is less than or equal to P by definition, we can draw the following figure. So this is actually a real simulation, and each square is like 50 experiments that my students did. So x-axis is the dimensionality and y-axis is the spike magnitude. So those two results tell me that there is a regime where neural networks and kernel methods both succeed. This is where the spike magnitude is too large. There is a regime where neural networks actually succeed, but kernel methods has to fail. Like they provably fail. They can, because of this if and only statement. And then there's a regime where they both fail. Now, the conclusion is basically that neural networks actually adapt to this low dimensional structure more efficiently compared to kernel. So this is a separation result between kernel methods and neural networks.
What is success in this case?
Risk to go below, like basically my learnability definition, right? So risk to go below some threshold. So these colors actually are the values of the risk. So like purple is kind of, I think, as small as it gets.
You draw the dash ones. These are like boundaries.
Yeah, so the boundaries are according to these magnitude. So this is like a log curve. So if you take the log, it's one, yeah, so it's that line. The exponent is defined.
These are derived,
What do you mean, right?
like how do you come up with this?
Well, it's based on, well, okay, so it's based on this figure that we estimate the exponent, but that only tells us the slope. It doesn't tell us like the exact line, so but you can actually play around and fit the exact line. So you're right, yes. So we don't have the explicit constants and everything, but it's basically like theorems already tell you the slope. Okay, so I'm almost done. So I'll finally interpolate between this idealistic regime and the no information case, and then that'll be the last thing I show you. In this case, I have an input that the direction of highest variance, mu, does not have perfect alignment between the unknown beta star. So let's see what happens in this case and how neural networks learn stuff. And in this case, actually, the question that we ask is, how does the performance of neural networks depend on the signal magnitude theta and the angle between mu and beta star? Okay, and in this case, I'm going to introduce two different parameters to control, basically, I mean, to simplify the exposition. The first one is gamma 1 that controls the alignment between mu and beta star. So gamma 1 equals 0 means you have perfect alignment, and gamma 1 large means you have no alignment, pretty much. And gamma 2 large means you have a large spike magnitude. Gamma 2 equals 0 means you have no spike. Well, tiny bit of spike. And the sample complexity of learning a target f star with information exponent k is as follows. So there are three regimes depending on how gamma 1 and gamma 2 interact with each other, and you get these sample complexities. So instead of staring at these equations and me trying to kind of make sense of them, let me show you what happens in the picture. So you get this three regimes depending on how gamma 1 and gamma 2 interact. Gamma 1 here is on the x-axis, that's the spike target alignment. Gamma 2 is the spike magnitude, that's on the y-axis. So let's look at the extremes. If gamma 1 is 0, so you have the perfect alignment. You see that this becomes 1. Now you're in this vertical line, you're always in the easy regime. So you get the nicest sample complexity. That's expected, because the perfect alignment is the easiest case. Now let's look at the other extreme, which I find quite interesting. If gamma 1 is 0.5, that puts you in this vertical line. So you start at the hard regime if your spike magnitude is small, but as you increase your spike magnitude, you can get to this easier regime, that's the intermediate regime. Now, why is that interesting? Because gamma 1 equals 0.5 corresponds to two independent uniform random vectors. So if you choose mu and beta star entirely independently from uniform distribution on the sphere, that is basically gamma 1 equals 0.5. Even though your spike is uninformative, you still get something if the magnitude is large enough. So uninformative spikes still provide benefits. That's what I'm trying to say. And then at any number, gamma 1 in between 0 and 1/2, you can look at the vertical line, and you're going to start with the hard regime. And if you have spike magnitude large, that's going to put you in intermediate, and then to the easy regime, which is kind of expected. So with that, I'll summarize what I told you. I told you about three different regimes of data model. Basically, one has the input has no information about the target. In this case, small learning rate, we show the precise impact of feature learning. Large learning rate, we show that neural networks can beat any kernel methods in this case. And then in the anisotropic setting, we show that neural networks adapt to this additional data structure a lot more efficiently compared to kernel methods. And we actually can provide a separation between neural networks and kernel methods. And the last one, we interpolated between these two and kind of showed three different regimes of sample complexity when it comes to learning with two-layer neural networks. So I'll conclude with one open question, which is quite interesting, that what I showed you with feature learning depends on one or few gradient descent iterations. But a lot of things change if you take more than a few iterations. Basically, if the number of iterations that you take, if it depends on the sample size or the dimension of the input, you can still perform a lot better than what I've shown you in this talk. For example, you see that my theoretical prediction is the solid curves, and these dots correspond to the empirical performance of two-layer neural network. So if you keep, and the x-axis is the number of iterations. So my prediction in these theorems actually work very well if the number of iterations is small. But as you increase the number of iterations that you take, the theory and the practice deviate, and actually you can go below the kernel golden bound, even with small learning. The number of iterations, the effect of optimization, is not represented in this talk and any of these works that I showed you today. And I think that's an interesting direction to study. So with that, I'll thank you and conclude, and happy to take questions.